Well, welcome to the 2.6 video for Math 126, 127. We're actually going to spend like 1.5 days on the 2.6 topics because there's a fair amount to recall here. This is information that you saw all in Algebra 2, but it's something that you haven't revisited in a while, and so you definitely are going to find that spending a little extra time on it will be of benefit to you. Okay, so we're looking at graphs of rational functions. In this video and some of the next video will be dedicated to that as well. We've talked about what it means for something to be continuous. So something is continuous if the graph is connected. A continuous function is going to visually look like this very connected graph with no gaps in it. And you could think of this as something that you can trace along the graph without lifting your pencil. And we'll talk more about continuity as we go through this course. So we'll come back to it. This is a description, and we'll get a definition of continuity later on, but not in this chapter. So if you see a prefix like this one, the prefix dis for discontinuity, this means something that is not continuous. So a discontinuity is a place where a function is not continuous. So a discontinuity is a location of a gap, if you will, in the graph. So if you're looking below, you might notice that this graph is not continuous. If I was trying to trace along it, I would have to lift up my pencil multiple times in order to trace along the graph. So this graph has quite a few places where there's a discontinuity. And there are a couple different types of discontinuity. The first type is a removable discontinuity. The second type is a non-removable, which could be described at times as an infinite discontinuity. Some non-removables are infinite. And so that's kind of like a big idea that we're going to be talking about. The first type is a removable discontinuity. A removable discontinuity is a hole in the graph, which we will plot with an open circle. And a hole in the graph with this open circle is going to be connected on either side. Connected on either side of the graph. So if I'm looking at this one, this is a hole in the graph. You might notice it is connected on either side of the hole, but we have that open circle. Same thing here, connected on either side, this is a hole. Something that is not a hole in the graph would be right here. This is going to have a different name. This is not a hole in the graph because it's connected on one side but not on the other. Okay, so this would be a hole here, here, and here. There are three locations in this one of a hole in the graph, and it's considered a removable discontinuity. Now, why is it removable? The reason that this is removable is in the equation. If I've got an equation of some function and maybe it's in a factored form like this, maybe something like this, you might notice that this could be reduced out. This is a location of a hole in the graph at the x value of -3. Now, a hole is actually an ordered pair, so we'd have to we'll learn how do we figure out where the y value is of that because it's an actual point. It's an ordered pair. But we're going to see that if we can take a factor that is repeated on the numerator and the denominator, that's going to tell us where a hole in the graph is. So if a factor is repeated on the numerator and the denominator, we're going to have a hole in the graph. A non-removable discontinuity, there's two types. The first type is a vertical asymptote. Sometimes this is also described as an infinite discontinuity. We'll talk about why in just a second. Or the last type of non-removable is a jump discontinuity, where the height literally jumps from one height to another. So if we go to this picture, we do have a vertical asymptote right here. Now, the reason a vertical asymptote sometimes is described as an infinite discontinuity is because what happens is the function will grow either to positive or negative infinity as we approach that vertical asymptote. That's why it's described as an infinite discontinuity in some textbooks. Now, let's see, how do you spell that? I tend to reference it as a vertical asymptote more just because that kind of fits the language that you guys have heard more in the past. But if you ever heard it described as an infinite discontinuity, that is still correct. We also have two jump discontinuities in this picture where we jump from one height to another. Right here, this is a jump discontinuity, and the other one is right here. So on this picture, we have 3 holes in graphs, 2 jump discontinuities, and 1 vertical asymptote as well. Now, a jump discontinuity often shows up with piecewise. It can also show up sometimes, oddly enough, in absolute value. You'll probably not explore that a ton this year, maybe just like with one specific instance. A vertical asymptote, actually in the example that I had earlier, this would be happening when we have a factor on the denominator, but that factor is not repeated on the numerator. Because if it is repeated on the numerator as well, then it's not a vertical asymptote. It is instead a hole in the graph. You might wonder, what about other factors on the numerator? Well, those are zeros. Those are x-intercepts. So all of those factors tell you information, but different information. Okay, so let's take a look at this one. We've got 2 examples here. The first one, we want to identify by using a graph all of the x values for discontinuities. We want to classify them. Are they removable or non-removable? And also, each one of those, is it a hole in the graph, a vertical asymptote, which could also be called as an infinite discontinuity, or a jump? So taking a look at this one, every place where we'd have to lift the graph is going to be a discontinuity. And I want to list the x values. So I first see there is a jump at 0. Now, a jump is a type of non-removable. So I want to list that and also clarify it as a jump. I'm going to list both those. Non-removable is like the category, and jump is how it looks on the graph. The next place where I notice a gap in the graph is at x equals 2. Now at x equals 2, is this a hole in the graph or is this a jump? Because it's connected on both sides, this would be called a hole, which is a type of removable. I have another one when x is 3. This is not a hole in the graph, although it's connected on one side, it's not connected on the other side. This is a jump, which is a type of non-removable. Please notice I'm categorizing it always as either removable or non-removable, and then saying what does it look like on the graph? What's the visual description? The last one I have is at x equals 4, and this is a type of non-removable because it is a vertical asymptote, which some people describe as an infinite discontinuity. I'm going to ask you for now to put both descriptions, vertical asymptote and infinite, and I don't remember which it says in your textbook for the Math Excel. Sorry, let me get that back. Okay, let's look at this one. For number 2, rather than a graph, what we have this time is we have an expression. And so we have to know what these factors are telling us. Well, first of all, if you ever see a factor that is repeated on the numerator and the denominator, that's going to tell you the location of a discontinuity. This is at x equals 5, which is the 0 for that factor. This is a removable. You can tell it's removable because I just literally removed it from my expression. I canceled it out. And that removable expression or removable discontinuity, the only type of removable is a hole in the graph. Any other zeros on the denominator will also give you a discontinuity, but notice I can't cancel that one out. This is a non-removable discontinuity, And specifically, this is a vertical asymptote or an infinite discontinuity. Those terms are interchangeable. Now, you might notice I didn't have one with a jump. That's because I don't have this piecewise function. I also don't have any absolute values, which you might be wondering, why would an absolute value be a jump? You're used to absolute values being a V, not absolute values are not always V's, which I know that's mind-blowing, but we'll explore that more. Okay, let's take a look at this next one. Related to the idea of discontinuities is the idea of domain and range. What happens with domain and range is we must exclude any places where we have a discontinuity. So for domain will be any x values that we want except for the locations of the discontinuities. And so what will end up happening is that we're going to have to exclude the x values of any holes or vertical asymptotes. And then for range, we need to exclude the y value of any holes, which you might wonder, how are we going to find that? Because I haven't told you that yet. And a new topic coming in is a horizontal asymptote. Now, interesting point. Horizontal asymptote is not considered a discontinuity for x values. Only for the range, only for y values. You might wonder why. Well, you can probably visualize that we have a horizontal asymptote right here along the x-axis. You can kind of see how this graph is turning. However, I still have x values that exist as we go along that horizontal asymptote. So there is not a discontinuity for x along horizontal asymptotes. Only vertical asymptotes is the only type of asymptote that would give me a discontinuity for x. Okay, so let's take a look at this. I want to find the domain of each of these rational functions. I want to be able to recognize key features from these rational functions. I should factor them if I can in order to figure those out. So let me factor any of these polynomials. Because as I factor, I might be able to recognize some things. So first of all, x is not allowed to equal -3 or +3. This one gives me a hole in the graph, and this one gives me a vertical asymptote. So when I'm looking at the domain of this function for a rational function, I can equal any x value except I'm not allowed to equal -3 or 3. Those are the only ones that x cannot equal. Now for the range, y is allowed to equal any value except not the y value from the whole of the graph, or if there's a horizontal asymptote, which we'll need to talk about here in a second. So how would you find the y value of a hole in the graph? Well, what we would do is we would want to rewrite this as an equivalent expression, because equivalent to this original expression is 1 over x minus 3 once I've reduced it down. And if I use this new one and I plug in the x value of the hole in the graph into my new expression, I can find out that the y value for my hole in the graph is -1/6. So I just met that one. Now I also need to think about horizontal asymptotes, which we've not talked about yet this year. We are going to talk about more, but you might remember that the degree is kind of important to determining horizontal asymptotes. This one has a horizontal asymptote at y equals 0, and that's because it has a larger degree on the denominator. We're going to review this in just a minute, but because of that, that is going to be a a range restriction. Okay, so this was from the hole in the graph, and this was from the horizontal asymptote. This was from the hole in the graph, and this was from a vertical asymptote. Well, let's take a look at this next one. I would want to start by factoring if I could, but this doesn't factor with real numbers. And when we're talking about domain and range, we're going to really be interested in the real numbers only. I'm not going to be interested in imaginary numbers like I would be for zeros. So I'm going to go ahead and not worry about the fact that this could only factor with imaginary. I'm not going to factor it at all. So what this tells me is that there are no holes in this graph because I don't have any factors that repeat here. So I don't have those as domain restrictions. Also, because there are no factors on the denominator, there is no vertical asymptote. So I don't have any holes in graphs. I don't have any vertical asymptotes. So my domain is all real numbers, which is pretty awesome. Sometimes you could write it using the kind of fancy R. Okay, but I don't have any issues here. All values of X will be allowed for the domain. Now for the range, I need to exclude any Y values of any holes in the graph, but I don't have any. I just need to be thinking about the horizontal asymptote. Well, the horizontal asymptote, anytime the degree is larger on the denominator, is Y equals 0. So I would say I can have all values of Y's except that Y value of 0. I'll skip that one. You might notice here that I'm using kind of set notation. I could use interval notation. It's actually a little cumbersome. The interval notation would be negative infinity to 0, and then union of that combined with from 0 to infinity. I think that's actually a little like less easy to write than the set notation, which is why I'm using set notation here. Okay, the vertical asymptotes. Just a reminder, vertical asymptote is going to be a 0 on the denominator, but we want to make sure that it's not repeated on the numerator. Because if it's repeated on the numerator, then it's actually going to be a hole in the graph. Because this is a line, we have to write this in the form x equals some constant. So like in this picture, we can visually see our vertical asymptotes would be at x equals -3 and x equals +3. That's how you would write them. Horizontal asymptotes. In order to determine the horizontal asymptote, we would be comparing the degree of the numerator and the denominator. If the degree is larger on the denominator, we're going to get y equals 0. In fact, you can see that on this one. That's kind of where it turns. A misnomer. Often people say, oh, a horizontal asymptote is a line that a function approaches and cannot cross. Often that's true, but not always. It will never cross it as we approach infinity. But in the kind of middle of the graph, it could cross it. And sometimes it does. Here's an example of where it does. Now, by the way, if the degree is the same on the numerator and the denominator, then the horizontal asymptote would still be at y equals some number. But what is that number? It's the ratio of the leading coefficients. Again, here's the form. If the degree is larger on the numerator, then we do not have a horizontal asymptote. You might instead have a slant asymptote. Might. Only if we have a larger degree on the numerator by 1. You can never have both a slant and a horizontal asymptote. You would have one or the other, or maybe neither. So if you want to find the equation of a slant asymptote, where that degree is 1 larger on the numerator than the denominator, only 1 degree larger, you can divide. Long division, or you could use synthetic division if it's set up where it's easy to do that. You'd have to use the 0 of the denominator. Can only be a binomial of degree 1. Here's an example of it. You'd have a remainder that you completely ignore, and the divisor that you get, or the quotient that you get, is actually the equation of a line. It'll be always a line, and it'd be a slanted line, which is why we call it a slant asymptote. So there's an example there for you. All right, let's take a look at these. We want to find the equations of any asymptotes on this one. So on number 5, you would want to start by factoring anything if you can, because you might have holes in the graph, and that'll help you find the equations of vertical asymptotes. So if I factor, now notice that we have a factor that reduces out. That is not a vertical asymptote, that's a hole. This one does have a vertical asymptote. The vertical asymptote would be at x equals +3. We do need the x equals, it is a line. Now, horizontal, if I want to check, I would look at the degree and see, is there a degree larger on the numerator or on the denominator? It's on the denominator, so the horizontal asymptote is at y equals 0. You might wonder, why is that? It's because as I start putting in like super large numbers, like 1,000,000, I start to get this the smaller number over this increasingly big number. And so if like I use a calculator and I start dividing small numbers divided by big numbers. And maybe that denominator just keeps getting bigger a lot faster than the numerator. And as I approach infinity on that denominator, I get really close to 0. This is scientific notation. Maybe I'll do one that's a little bit less extreme, but you can kind of start to see it. Notice I'm getting closer to 0. So that's what's happening. You have this smaller number divided by this increasingly large number, and so you approach 0. Now, we cannot have a slant asymptote in this problem because I have a horizontal asymptote, and you can never have both. By the way, you don't actually have to have either. Not all problems have horizontal or slant asymptotes, or even vertical. So you got to look and make sure they meet the requirements. Okay, taking a look at number 6. This numerator is not going to factor for me. I can kind of tell just by how kind of bizarre it looks, but the denominator will. So I am going to factor out that denominator because that can help me, and I'll reorganize this in descending form. This can help me identify maybe my vertical asymptotes. I might also want this in descending form. It might help me with factoring it. I'm going to take out a GCF of negative 5x squared. I'll take out a negative since my leading term is negative. And I'm left with 2x minus 1. Now, both would be equations of vertical asymptotes. And that's because I don't have those factors repeating on the numerator since my numerator doesn't factor. So I have a vertical asymptote at x equals 0 because that is the 0 of a GCF. You want to think about like what is the value of x you could substitute in to make that portion of the equation 0 out. And here the vertical asymptote is at x equals 1/2. So there are 2 vertical asymptotes. Horizontal asymptotes, I want to compare the degree. So on the numerator is degree 3. On the denominator is also degree 3. So my horizontal asymptote will be found at y equals, horizontal lines start with y equals, and I'm going to make a ratio of the leading coefficients on the top and the bottom, those coefficients of the x cubed portion, and I want to reduce it down. So my horizontal asymptote is at y equals negative 6/5. Because I have a horizontal asymptote, I do not have a slant asymptote. All right, taking a look at this one. Does this factor? Maybe. Let's just try it and see if I could get this numerator to factor. I would have a 2x and an x. My factors of 7 are only 1 and 7. Those are my only options. So I want to see, could I arrange them so I could get a negative 5? When I FOIL it out, yeah, I could. So this is how that would factor. If you need help with factoring, please see your teacher. You do need to know how to factor. There's lots of different strategies, so your teacher can give you some strategies. It is helpful to factor this just because I want to see if any of these factors repeat. They don't. By the way, what are these ones? These are x-intercepts, which are not going to come into play when I'm looking at asymptotes, but that's what those are. So since I don't have any factors that cancel out, I don't have any holes in the graph, so this would be a vertical asymptote right here at x equals 2. And then if I want to look for horizontal asymptotes, I would compare the degree. This has a degree that's larger on the numerator than the denominator. What that means is that it's growing faster on the top than it is on the bottom, and we aren't going to have this like kind of reducing down to get to a specific number, so there is no horizontal asymptote. That means we might have a slant asymptote. The way you would know is the degree of the numerator exactly 1 larger than the denominator? And the answer is yes, it is. So for my slant asymptote, I'm going to divide these. I'll use synthetic division because this binomial is really easy to find the 0 for. So I'm going to use synthetic division and divide this out. And I won't care about what the remainder is. So I get, I'll bring down the first number. Remember, you multiply and add, multiply and add. I don't care about the remainder at all. For my slant asymptote, I just want the equation of the line that's left, which is y equals 2x minus 1. Your slant asymptote will be a line. Should be in the form y equals mx plus b. Okay, so there's different ways to kind of explore those asymptotes. Notice they're all equations. They have either an x equals or y equals. Vertical would be the ones that are x equals. Horizontal and slant are y equals. Well, there's some other important things that can help us when we're graphing rational functions. The x-intercepts are the zeros of the numerator that do not repeat on the denominator. Remember, if they repeat, those are holes in the graphs. The y-intercept is the value of the function if you substitute in a 0 for x. And holes in the graphs are those factors that repeat, and on the numerator and denominator we can cancel out. So sorry, this is my little handwritten example for you because I couldn't quite find what I was looking for from the internet. So here's an example. Now I have everything all factored. Once things are factored, those are how we find important things. If a factor repeats, that's a hole. Factors on the denominator that don't repeat will tell you a vertical asymptote. Factors on the numerator that don't repeat will tell you the location of x-intercepts. So my x-intercepts come from those factors on the numerator that didn't cancel out. So those would be ordered pairs at 0, 0, and 7, 0. To find the y-intercept, I could go to my original problem and just plug in a 0, do a little computation to simplify. Turns out that this y-intercept's at 0. That's because anytime an x-intercept is at 0, so is a y-intercept. If you think about that, that point at the origin would intercept both the y and x-axes. So there's my x and y intercepts. There's a hole in the graph when x is -2. To find the y location of the hole, you would use the reduced down form and plug a -2 in. So this has a hole in the graph at -2, -18, wherever that is. So those are a couple important points on the graph. We can use those to help us with the graphing along with your vertical asymptotes and so forth. Like this one has a vertical asymptote at x = 1. And a horizontal asymptote as well. The degree on the top is 3. On the, oh, no, I guess not. This one has a slant. Okay, so we can explore that one a little bit more if we want to, but we're going to kind of get to graphing in a minute. All right, so on this one, we want to find those important values of x and y intercepts and any holes. These are going to be coordinates here that we're going to be finding. So I want to start by factoring anything that can factor. Now, each of these factors tells me something on the graph. Factors that cancel out tell me that there's a hole in the graph. This would be an x coordinate of -2. To find the y coordinate of this graph, of this hole in the graph, you would use the reduced down form and plug in the x value of -2 to both the top and the bottom and simplify that, and I get -4 over 1, or -4. There's the location of the hole in the graph. The remaining factors are also going to be important pieces of information. The remaining factor on the denominator is a vertical asymptote. However, they did not ask us for that, so it's not technically part of the answer, but it's okay to know what that is. And then the remaining factor on the numerator is going to be an x-intercept at the 0 of that. 2, 0 is how you'd write that as a coordinate pair. Notice the x value is a number. The y value is a 0 because I'm at a height of 0 in order to be along the x-axis. So there's some kind of important points here. We also were asked to find the y-intercept. So to find the y-intercept, plug in a 0. Now you could plug it into the original equation. You could plug it into the factored form. You could plug it into the reduced out factored form, which I think is actually the fastest. So if you plug in a 0 here, you would get -2 over 3. So we have a y-intercept somewhere along there. Then they start to help us form the shape of our graph. And by the way, this is a vertical asymptote. Here you might kind of start to go, oh, maybe I can start to see some things. Okay, when we're graphing rational functions, things are going to be easiest to see if something is factored. Anytime things are factored, we can start to find a lot of our important information. I would usually start by drawing in the asymptotes. Consider horizontal, vertical, and slant. Okay, I usually do that first. Now remember, you would never have both a horizontal and a slant. You'd have one or the other, or even neither, which would be rare, but that can happen. You're going to draw them as dotted lines. They're not actually parts of the graph, but they're boundaries that will help you shape your graph. Then we'll look for the coordinates of any holes in the graph, use open circles. We can also, I didn't put this on here, but you could plot any x-intercepts. Those can be helpful as well. And then we can also, if we want, use an XY table to get us a couple more points if we feel like we need it. And then we can sketch the curve, make sure we're bounded and approaching any of those asymptotes. Okay, so for this one, I will start by factoring this. Now the numerator is a monomial, so that's already considered to be factored. I do not have any factors that repeat. I don't have any holes in the graph. But I do have some vertical asymptotes. My vertical asymptotes come from those factors on the denominator that are not reduced out. There's 2 of them. Both of them need to be listed with their own x equals. Please write them out as 2 separate lines. I'm going to draw them in as vertical lines on this graph. Now this little kind of like set over here on the left of important information will kind of help guide your process of graphing, so you kind of know what are the important things I should have. Horizontal asymptotes we can find by comparing the degree. Well, these ones have the same degree. Since they have the same degree, the horizontal asymptote, which is y equals, would be the ratio of those leading terms 2 over 1, or y equals 2. That's a horizontal line right here. Since I have a horizontal asymptote, I cannot have a slant asymptote on this one. I'm going to come back to domain and range and x and behavior in a minute. I'm just going to look at the y and x intercepts. To find the y-intercept, plug in a0 into your equation. I'll use the factored form. You don't, I guess it doesn't matter. You can use the non-factored form. Doesn't matter. It'll work either way. I end up with 0 over something, which is just 0. So my y-intercept is at 0. I probably could have figured that out because this is my x-intercept up here, and that one's also at 0. So we can write these as ordered pairs if we want. They're actually the same point. This is the only time that we're going to cross the x-axis. We cannot cross it any other time because there's no other factors on that numerator. So just kind of keep that in mind. Okay, now if I graph this, kind of think about like what might be happening on this graph. If you need a couple more points, go ahead and plot them. You can. On the, like one idea is to kind of plot like a point or two in each region. So like if I plot to the left of -3, maybe I pick something like -4 and just substitute that in. You could do the factored or non-factored. It doesn't actually matter. You'll get the same answer. I would get, let's see, 32 on the top. On the bottom, I'd get -1 times -7, so over 7. Like, what is that? It's like 4-ish. So at -4, I'm at a height of around 4-ish. Well, I'm not going to cross these horizontal and vertical asymptotes in like the ends. Maybe in the middle I would, but not in the ends. So this would be something like this. Now, in the middle, I could cross that horizontal asymptote. It can happen in that interior region. So I'm going to go ahead and just kind of double check that. Maybe I'll pick like a -2 and just kind of see. I'm going to just pick a number on kind of close to either side of these. I'll do -2 and +2. I just want to see what happens. If I plug in a -2, I'll just do some computation really quickly here. I'd get 4 times 2, which is 8. And on the bottom, I'd get a 1 and a -5. So I get like -1.6. I kind of want to see what's happening over here close to this one as well. So I'll plug in a 2. I still get an 8 on the top. On the bottom, if I plug in a 2, I get a 5 and a -1, which is another -5. So it doesn't look like I'm crossing this. I could. Sometimes you cross. Sometimes as you plot some points, you find out that you're going to cross. You really should test some points because you don't actually know if you're going to cross that horizontal asymptote or not until you test some points. Okay, over on the right side, I'm going to just get something past the horizontal asymptote or the vertical asymptote of 3. So I'll plug in a 4. Again, I'll get a 32 on the top On the bottom, I'll just use the factored one. 4 plus 3 is 7 times 1. So this is a little over 4. 4 point something. There's my sketch. Okay, now domain. Domain, you might vaguely remember from what we kind of talked about earlier, is all x values except not the ones where there's any vertical asymptotes or holes. Now this one doesn't have any holes, so I will not worry about that. Range will be all the y values except not any y values where there's holes in the graph, which I don't have, or horizontal asymptotes. And behavior, if I kind of look at what's happening on the far end, see how these are turning sideways? For end behavior, we approach the horizontal asymptote on both the left and right side. So we can write this in a conic compact form, both on the right and the left side. My function h is going to approach whatever height is the horizontal asymptote. And that will always be true for these rational functions. If there is a horizontal asymptote, that's the height that will be approached for the end behavior. All right, example 10. Again, I'm going to be graphing this. I'll start by factoring. I have a GCF on the numerator and a difference of 2 perfect squares on the denominator. Any factors that cancel out will be holes in the graph. So I have a hole in this graph. And the x-coordinate of that hole is at 1. To find the y-coordinate, I'm going to use the reduced down form of this graph, 3 over x plus 1. Don't use the original one. You'll get a 0 over 0, which is not something we know how to interpret. But so this would be 3 on the top, and when I plug in a 1, 2 on the bottom. So the hole in this graph is at 1, 3 halves, or 1.5. However you want to write that, doesn't matter to me. You're going to plot that as an open circle. Well, any remaining factors on the denominator would tell you the location of vertical asymptotes. So in this case, at -1. Remember, vertical asymptote is not actually a part of the graph, but it's a boundary that we will use to help with the graph. Horizontal asymptotes, if I compare the degree, if the degree is larger on the denominator, then we have a horizontal asymptote at a height of 0. We do need the y equals. This is a line, so it must be written as an equation. If there is a horizontal asymptote, there is no slant asymptote. A y-intercept can be found by substituting in a 0 into the function. I'll use the reduced out form, although we could use the factored or original. I would get 3 over 1, which is 3. And then if I want to test some points, on the right-hand side, I don't really need to test points. I have some points already on this right-hand side. I can kind of tell what's happening here if I kind of approach my asymptotes. It is possible that I could kind of cross my vertical asymptote or my horizontal asymptote really close to here. I won't later on. Typically, we're not going to give you ones that do that on those like exterior regions, although just know that it could happen. The only way you would tell is by testing a whole bunch of points. And then I am going to want to test something on the left side of this because I don't know in this region will I be above or below the horizontal asymptote. So maybe I'll test something close to the vertical asymptote. I'll test like -2. I'll plug that into the reduced form and I get 3 over -1 or -3. This is far enough away from my horizontal asymptote that I'm thinking I probably am not going to be crossing this, but I don't really know for sure unless I tested more points. But I'm feeling pretty good about this. I could test more points if I wanted to, like -4, -5. Again, we're really not going to give you ones that do that except for maybe in an interior region if you have multiple vertical asymptotes. All right, so the domain. The domain, x is every value but not the vertical asymptote or the x values of any holes in the graph. Now, usually it's considered like best to write these from smallest to largest, these numbers, although I doubt anyone's going to mark you down if you don't, but that's usually how it's written. Range, we could be any y values, but not the y values for horizontal asymptotes or for holes in the graph. So look for these y values of these special points. Those need to show up in the range as things that we're going to reject. We found out that the y-intercept is at 0, 3, which I already plotted. The x-intercept would be any zeros on the numerator that are not from holes in the graph. Well, if I looked at my reduced down one, there's no way for this numerator to ever equal 0 because I don't have an x. So there is no x-intercept. This is great news actually, because if there's no x-intercept, I can't ever cross my horizontal asymptote. So that's a nice way to know that I'm not crossing that. And behavior, we can kind of look and see how this is turning sideways. We will approach the horizontal asymptote height from both the left and right side. Notice that this is a g of x. Okay, so I don't want to write f of x. I'll use the notation given and how this was named. All right, we've got one more to look at. On this one, this is going to be kind of an unusual one. This one doesn't factor. My numerator is a sum of perfect squares rather than a difference. It doesn't factor with real numbers, and when we're graphing, we're going to use real numbers for these rather than the imaginaries. So I do have a vertical asymptote here at x equals 2. So I'm going to draw that as a vertical line. Horizontal asymptotes will come from comparing the degree. But if I have a larger degree on the numerator rather than the denominator, I do not have a horizontal asymptote. So what about a slant asymptote? This one will have a slant asymptote, and that is because of the fact that I've got 1 degree higher on the numerator than the denominator. I'm going to use synthetic division. Be careful to insert a 0 for the linear term. Make sure that any skipped powers of x are represented. All right, so if I use my synthetic division, remember we don't care about the remainder, we ignore it. This would be the line y equals x plus 2. So use your knowledge from Algebra 1 to graph this. The y-intercept is at 2. The slope is up 1 and over 1. We will draw this with a dotted line because it is still an asymptote. Okay, so for the remaining parts of this, all right, let's see here. I want to look for x-intercepts. Well, on this numerator, because it doesn't factor with real numbers, there are no zeros on the numerator. There are no x-intercepts. We will never touch the x-axis on this. Holes, we didn't have any factors repeat, so there are not any. Now to actually draw in the graph, I'm only going to be in one region for each kind of like little vertical space, but I need to find out where. So let's pick a couple points on either side of my vertical asymptote. Maybe I'll use 1. Since this doesn't factor, I will just use the original and plug that in. I would end up with a 5 on the top, -1 on the bottom. So at 1, -5. 1, -5. So I'm in this region. Oops, +1, -5. I'm in this region down here bound by these. So it's gonna, I don't know exactly where that mountaintop is here, but there's gonna be, in order to kind of fit this, something like this. I would need to use either a calculator or maybe some calculus that you guys haven't learned yet to find out exactly where that mountaintop is on this part. And so we will use a calculator in a minute to kind of figure that out. That's going to be helpful as we do our domain and range. Let's see, I want something on the other side of the vertical asymptote, so maybe I'll text x equals 3. I'd end up, let's see, 3 squared plus 4 is 13 over 1. So this is all the way at 313, way up here. But I can tell I'm in the top region. So something like that. So the y-intercept can be found by plugging in a 0, which can be helpful. If I plug that in, it just gives me a couple more points. I'd get a +4 on the top and a -2 on the bottom. Hey, I kind of just guessed that and got lucky this time. Okay, so there's my y-intercept at 0 for x, -2 for y. Now drawing in like the domain and range, doing the domain and range is actually, well, especially the range, is kind of tricky with a slant asymptote. So we'll talk about that. Domain's not too bad. I can just use my vertical asymptote as a domain restriction. I don't have any holes in the graph. Range is going to be tricky because I'm going to need to use the graphing calculator to help me with this. But let's just talk about the end behavior really quickly. On this one, the end behavior as x approaches positive infinity, I have different behavior than I do on the left. Y, which is how I've named my output, goes up forever. So that would be positive infinity. On the far left-hand side, as x approaches negative infinity, y is going down. It's kind of going like left and down, but it's for the y value for the heights, it's going down. Okay, so what about the range? I'm going to have to use a graphing calculator for this. I do not have an option. So let me go ahead and get this graphed. So on the numerator, I had x squared plus 4. Make sure you group those in parentheses. On the denominator, I had x minus 2. And let's see, this should kind of match. I'm having a hard time maybe seeing this. You could certainly adjust the window to say maybe we want to just see a little bit more. Maybe we'll even jump by 2s for the y's to kind of be able to see it. Oh, I guess I changed the x's and not the y's. Let's try that again. I just want to be able to get a little bit more visual, kind of confirm what I found by hand. Looks good. This is about what I found by hand. Now, what's happening with the range is I have this like gap in my problem where I do not have any information. I don't have any information in here. So sometimes we wouldn't ask you to find the range unless you had a graphing calculator. We wouldn't ask you to do the range. But on this one, we do want to make sure I kind of am exploring this range. So here's what I'm going to do is I'm going to find out what's the top height on this kind of like little mountaintop here. What's the lowest height on this valley? So on your graphing calculator, we can use calculate, which is above the trace button. So I'm going to do second calculate to find the maximum and minimum. So I'll find the maximum of this left side. I want to start by being a little bit on the left side of that mountaintop, scooch over to be on the right side of the mountaintop. Looks like at negative 1.657. So negative 0.8 and negative like 1.7, I'll call it that. That's where this is. Okay, that's about where that is. It's actually like a little bit off from where I thought, but not totally off. And then for the other one, I'll find this minimum here. So second, calculate. I'll find the minimum. So I'm just going to arrow over. Calculator is going to jump past that horizontal asymptote until we can kind of see it again. Get to the left of the valley here. Scooch past the right, make sure we've started to climb back upwards again so that you trap that minimum. It looks like 4.8 and 9.7. So at 4.8 and 9.7. So what does that mean for the range? Well, what this means for the range, and I'm going to actually write this in interval notation. I think it's a little easier. I'm going down from negative infinity up to this negative 1.7. And then I have a gap. This union here symbol is just like saying like there's this gap. Let's jump to the next part. And then I'm going to go from this next height that's from 9.7. I'm just looking at the heights that exist all the way up to positive infinity. There's a couple other ways to express that. And so you might explore that, and there's different ways to express that. It's kind of a unique question to ask the range for this one. And that is the end of this video.